Welcome to this explainer. Today, we're diving into a story about how an unsung hero stepped up to solve a massive existential crisis in physics, and in the process, well, she completely reshaped our understanding of reality itself. We're going to be looking at the life and the incredible work of Emmy Noether, a mathematician who basically found the hidden threads that tie our entire universe together. So, let's set the stage for this massive mystery that was totally stumping the greatest minds of the early 20th century. Picture this. It's 1915. Albert Einstein has just introduced his general theory of relativity, which, is a towering achievement. But there was a glaring, actually terrifying problem lurking right there in the math. General relativity seemed to completely shatter the law of energy conservation. The absolute, non-negotiable rule that energy cannot be created or destroyed, yet suddenly looked like it was falling apart.
Okay, so here's exactly why this crisis happened. Einstein's new theory revealed that space and time are not just this fixed, static stage where the universe plays out. Instead, space and time can actually curve and expand and stretch. But this shifting background meant that local energy density was changing. Think about classical physics, like drawing a box. The energy going in absolutely must equal the energy coming out. But in general relativity, because the box itself is warping, that classical law suddenly fails. The brilliant mathematicians over at the University of Göttingen, David Hilbert and Felix Klein, were just completely stumped by this apparent failure. To save relativity, they knew they needed help.
Enter Emmy Noether. In 1915, this 33-year-old fiercely brilliant algebraist arrived on the scene. Hilbert and Klein fully recognized her unparalleled knowledge of invariance, and they literally called her to Göttingen specifically to fix this massive hole in Einstein's theory. But, as you might guess for the time period, her arrival was anything but easy.
Get this, despite her undeniable genius, Noether faced immense discrimination. The faculty fiercely objected to hiring a woman, actively blocking her from officially joining the university. She was literally forced to work unpaid, initially giving lectures under David Hilbert's name. Frustrated by all this resistance from the historians and philologists at the university, Hilbert famously delivered the scathing defense of her right to work, basically saying, "We are a university, not a bathing establishment." Ultimately, she persevered and spent the next 3 years prodding the exact fault lines separating physics and mathematics.
Now, before we look at her monumental solution, we really need to understand a core concept: symmetry. In mathematical and physical terms, a symmetry is just an action, or transformation, you can perform on a system that leaves it completely unchanged. Think of an equilateral triangle. You can rotate it by 120 degrees and, well, it looks exactly the same. Or, over in the world of physics, it's the idea that you can perform an experiment right here, then move, say, 10 meters to the left, perform it again, and your fundamental results won't change at all. So, keeping that in mind, let's look at her first theorem, which is where she brilliantly unveils the deep, deep connection between those symmetries and the laws of conservation.
This was the first half of her groundbreaking 1918 publication. Noether realized that symmetries actually constrain how a system can behave, and out of the math, a quantity just pops out that literally cannot change. Notice how specific continuous symmetries mathematically guarantee specific conservation laws. Because the laws of physics don't change as time passes, which we call time translation symmetry, energy is conserved. Because the laws don't change from place to place, that's space translation symmetry, linear momentum is conserved. And rotational symmetry, that mathematically guarantees the conservation of angular momentum. It's like a giant, beautiful puzzle perfectly snapping together.
The impact of this is absolutely staggering. As the physicist Feza Guerzi pointed out, before Noether, energy conservation was really just treated as this mysterious empirical fact. We just accepted it because that's what we observed. But Noether proved that conservation laws aren't just these arbitrary axioms of the universe. No, they are the inevitable mathematical consequences of the universe's underlying symmetries. She literally pulled back the curtain on reality.
But to solve the Einstein paradox, we have to contrast her first theorem with her second theorem. So the first theorem applies to global finite continuous groups. That just means the symmetry transformation is the exact same everywhere, which gives us those proper localized conservation laws like energy. But general relativity, that relies on something called local infinite continuous gauge symmetries. Because spacetime is curving and stretching, the transformation changes from point to point. Noether realized this shifting background requires a completely different mathematical rule, leading to what Hilbert called improper conservation laws.
And that incredible realization brings us straight to her second theorem,
which finally resolves the massive energy paradox of general relativity once and for all.
Let's look at how she ultimately saved Einstein's greatest achievement from collapsing under the weight of its own math. In her 1918 publication, Invariant Variational Problems, she mathematically proved that the apparent failure of local energy conservation in general relativity wasn't a flaw in Einstein's theory at all. Actually, it was exactly what the math demanded.
Here is exactly how she solved it. Noether proved that when you're dealing with infinite continuous groups, like the local gauge symmetries in general relativity, the inherent flexibility of that system creates mathematical relations between the equations of motion themselves. These are known as Bianchi identities. She completely validated Hilbert's hunch. In a curved, shifting spacetime, you simply cannot have a proper localized energy conservation law. Instead, energy just transfers to and from the gravitational field itself. So the lack of traditional local energy conservation? It isn't a bug, it's a fundamental, characteristic feature of a gauge theory. The paradox was entirely resolved.
The really crucial thing you should take away from this is that her breakthroughs didn't just patch a hole in relativity, they laid the absolute bedrock for a century of modern physics. Her second theorem's focus on gauge symmetries basically became the blueprint for the entire quantum world. By the 1960s and 70s, physicists were relying on these exact principles of gauge symmetry to unify the electromagnetic and weak forces and to build the standard model of particle physics. For instance, a symmetry in the electromagnetic field is exactly what forces particles to conserve their charge. It's all connected.
Einstein himself was just in absolute awe of her. After she passed away way too early in 1935, he wrote this incredible tribute. He fully recognized her unparalleled mathematical creativity and intellect, especially when you consider the extreme societal adversity, the prejudice, and the total lack of pay she endured for most of her career. As her close friend Herman Weyl noted, she was really a chunk of human primary rock.
And her work is far from just some historical footnote. Modern mathematical physicists, like John Baez, constantly remind us that we're actually still unearthing the profound depths of Noether's insights. Every time we push deeper into the quantum realm, or look out into the expanding cosmos, where, by the way, the universe's expansion actually breaks time translation symmetry, meaning cosmic energy is technically not strictly conserved, we are still relying on Noether's mathematical framework to make sense of it all.
So, as we wrap up this explainer, I want to leave you with a bit of a challenge. Emmy Noether taught us that the rules governing reality aren't just arbitrary, they are the physical manifestations of pure geometric elegance. So next time you look out at the world around you, how will you perceive the beautiful hidden symmetries that are shaping the very reality you're experiencing right now? Thank you so much for exploring the genius of Emmy Noether with me.